2 or 3 days, depending on if we have school Friday too. Don't know. I'm not anticipating to see you again after today. But in case we do, you know, that's great and all. But I've made plans accordingly. So write down the nuclear chemistry summary table from what you should have gotten from your reading guide that you guys did, the video reading guide. Also, concept 6, stand your desk the whole day, nuclear reading guide, video guide, stand your desk the whole day.
I would do this. Like after the years through all of the years, you cut me off and
Were you going to do YouTube like classes about it?
yeah.
Did that make sense? I think
Well, I think I'm one
Yeah, copy that down. I'm trying to give you a quick summary of stuff. So, yeah, IQ concept 6 on your desk and the nuclear reading guide. So, do you guys have, let me pick that up. So, you guys have a good basis of your nuclear chemistry knowledge. Today we're going to go through about 10 slides of notes on the rest of it and do like 2 problems on half-life. And then we're going to solve some more problems on how to write out these nuclear decay equations. After that, we have a Skittleium lab that has a lot of practice built in, and it's got some math involved, and it's got some candy involved, so right, you can complain. And I will go ahead, I'll go over that in a second. I don't know when my juniors are leaving, so I have to go through quickly, and then I'll recap. And if you are a junior and you leave me, you have to watch this video. It's a necessity. Okay, so, what's up? The test is whenever I see you again. What? Oh, okay. So alpha, I'm going to turn these lights down just a wee bit. Alpha decay has the biggest portion of the nucleus that is removed. So far this whole entire unit, we've been going, nucleus doesn't change, nucleus doesn't change, nucleus doesn't change. There's the special case of nuclear decay, which means nucleus decays, right? That it does change, and that's what these particles that we see, alpha, beta, and gamma, those are the things that are being given off out of the nucleus. So we have totally lied about the nucleus not changing, okay? So 95% of the time the nucleus doesn't change, but in this case it does. So alpha decay, this is what pops out of the nucleus. It's called a helium atom because it's an atom of, it's essentially the mass and the size of a helium nucleus. So what does the 4 up here mean? I hope everybody's writing this down because I'm not going to wait for you to write this down, people. Let's go. I should see you writing. What does the 4 mean? I hear you, thank you, mass, and the 2 means proton number. So that's why we call it the helium nucleus. It's mass to charge, it's like we just said, 4 to 2, that's what that, the isotope nomenclature up there says. And then they're huge, you know, in comparison to everything else, beta particle and a gamma particle, they're huge. They weigh a whole 4 atomic mass units, okay? So, since they're so huge, you can block them with clothing. You can block them with paper. So if I'm shooting alpha particles at you, just kind of like block me with your clothes or some paper. Nothing, you can't touch this, right? The only thing you don't want to do is get alpha particles in your mouth. So don't open your mouth when I'm shooting alpha particles at you, because they'll go inside of your body and do some damage. So, but we are constantly bombarded with stuff like this, and our bodies do a really good job of neutralizing those kinds of hazards. But that's really easily blocked. Beta particles. Alpha has this weird symbol. So like a fish, right? So the alpha particle is a fish. The beta particle has a symbol of a bee, but it's got this little tail, like a long tail on the end. Or it looks like this, because a beta particle is essentially a really energetic electron. So what happens in the nucleus when beta particles are ejected or decayed, the nucleus does a little switcheroo. It has like a proton and a neutron, and they kind of do some changing up of what they look like, and when that occurs, it spits out an electron. So what you basically need to know when I say beta particle emission or beta particle decay, an electron is popping out of the atom. I know you're going, well, it's a nucleus. A nucleus doesn't even have an electron, right? The nucleus only has protons and neutrons. But like I said, the protons and neutrons do a little switcheroo, and they shoot out an electron. So that's upper level chemistry, though. So I'm just sticking with this explanation. So notice though that the mass of this thing is 0 because there's no, zero number at top. And so what happens is this -1 causes the proton number to increase, actually, because it's changing the nucleus. So this is actually an increase in mass with the proton, and I'll get there and when we do some nuclear decays. So mass of charge 0 to -1. So you need like aluminum foil to block those. Those are a little bit more potent because they're small and they can get through your skin and through your clothing or through paper, so they're smaller. Last type of nuclear decay particle, I say particle, but it's not really a particle, is just straight up energy, people. It's gamma rays. So this is just energy. I don't really have a mass to charge kind of notation for you because it doesn't have one. It's like an upside down fish, or it's kind of more like a Y. It's like that, but that's like a Greek letter that's I always murder when I try to draw it. So that's what gamma ray emission looks like. No mass issues to deal with. It's just straight up energy. And so that's like very energetic. It will get through clothing, it will get through paper, it will get through aluminum foil. You need concrete, get like 2 feet of concrete, or lead. Lead does a really good job of capturing that energy so it doesn't penetrate your body. Because we all know if you get gamma radiation, you're going to be the Hulk. You know this. Okay, so that's we try to like really limit the superheroes. There's only so many people that can rule the earth. Okay, so let's do these based on what we know of our particles. So this was the first one on your reading guide, so that's why I want you to keep it on your desk so you check it as you go. Carbon-14 undergoes beta decay. Undergoes beta decay means carbon-14, which what's the number down here for carbon? 6. And you don't have to memorize that. You have the periodic table in front of you that says carbon's atomic number is 6. Undergoing beta decay means beta decay is given off. Beta particles are given off. So what does a beta particle look like again? 0, -1, and an electron, right? Or you could, instead of putting E there, you could put a B, because the B is the same thing as me saying a electron. Okay? Plus, something else that is the transmutation. It's transformed from carbon to a new element. Because remember, when we change the nucleus, we got a whole new element we're talking about. So this 6 must equal whatever is on the product side of this equation, because the law of conservation of mass still occurs. Whatever we have, we end with, it's just changing the way it looks. So we're literally changing the element in this case. So -1 plus something has to equal 6. So what's the something? 7, okay? So 7 is going to be the atomic number. And then we have 14 equals 0 plus something. So what's that one? 14 as well. So who is this new element that we've made? How do you know nitrogen? Because yeah, it's the atomic number 7. You just look on the periodic table, like, who is this? You just look for number 7, and that is nitrogen. So does that one make sense? Yeah? All right, so the beta ones are a little harder because you got to go, -1, you got to do your math easily. So let's do an alpha one, though. So we have iodine 125 undergoes alpha decay. So iodine 125, what's the atomic number of iodine? Say it again. Oh, I'm sorry, it looks like an 8. 53 undergoes alpha decay. What's alpha decay's particle symbols? 4/2, and that's, I'm going to call it a helium nucleus. That's sometimes how you'll see it. Or, like you'll see it with He, or you'll see it as alpha, like that. I'm just going to go with alpha because that's called alpha decay. So, plus something else that completes the system. So 125 is equal to 4 plus something. What's that something? 121. So that's the mass of the new particle, the new isotope that's made. And then 53 is equal to, so this arrow in the middle kind of seems like an equal to, 2 plus something. 51. Good. So 2 plus 51 is 53. So whatever's on the reactant side must equal whatever's on the product side. The product side is just rearranged a bit. So who's atomic number 51? SB? Antimony? There you go. It's really actually very easy. It's just the only part you got to know are what in the heck is an alpha particle, what in the heck is a beta particle. That's really only new stuff. The rest of the stuff is just isotope, isotope, isotope notation. Okay?
And then teachers, please pardon this interruption. At this time, we are going to begin the pre-administration for the ACT for juniors. Last name A through J.
A through J.
If your last name is A through J, please report to the cafeteria at this time. Thank you.
So, my juniors, I don't know when you're coming back. Take your stuff. Those only A through J. Now, everybody listen to me now. Because we're getting behind in terms of snow, I'm actually going to try to do you a favor. Because it's hard to remember stuff we did like 3 weeks ago. Every day we're out. I have the free response part of the test for you to take home. So please, please, please get 100 on this section. Like this free response is one of the hardest free responses we have all year. So I'd rather you do it in class, but I'm okay with you doing it at home if it's going to help your grade. You will take the multiple choice in class 45-ish minutes the day you get back, okay? So you can see juniors, complete unit review, that should be like 90% done. You've had that for 2 years at this point. Free response, this, and reading guide 9, because after we do the multiple choice, they gotta see you again, we're gonna start nomenclature, which is talking about stuff in chapter 9, so you gotta have a little bit of a basis, so I'm not talking gibberish to do that today, okay? Because I guarantee you will not see tomorrow. So those things, write down, pick up the free response on your way out. Peace. No, I'll take it the day you get back, because I'd rather you study. If you guys have your stuff, I'll give you your full credit. But you got to study. Okay, so to grab it for response, please do not forget that. So I don't know. I'll post it on my website too. Have fun at your ACT meeting. If I see you when you get back, I'll see you when you get back. Watch the video later. Bye, juniors who are in A through J. All right, the rest of us, we're going to do this last one together. Our juniors A through J. Oh, you're beautiful. Thank you. All right. Hey, you guys can scooch closer. You can stay where you are. Either way works for me. Okie dokie. So let's go through this last example, and then we'll go through some examples on half-life. All right. So gamma ray emission. Gamma ray emission does not change a single thing in the mass or the proton number. So we just write down what we have. Nickel 56. What atomic number is nickel? 28. Thanks, Ashley. Bye. And then it undergoes gamma emission. So what's happening is it's just some excess energy is given off. Here's that excess energy. That's what we call energy, gamma ray. And then nothing changes on top and bottom. So this is still nickel 56, but it's just a little less energetic. It's more stable, just because a little bit of excess energy was given off. So those are the 3 versions of the atomic, or the bounce chemical equations you would have to write for nuclear decay series. Thumbs up, you ready? Okay, most of us look good. Okay, so the rest of this, and this is just the same, paper, wood, or aluminum foil, and then concrete. Those are the types of symbols. You know, that's kind of like a Y symbol there. The only parts I really want you to look at or write down, because the rest of it you should have background information from your reading guide that you did, are the highlighted sections, okay? So like we just said, Dalton, who proposed initially that the insides of the atom are not going to change, they're indivisible, is a flat lie now, because we know a lot about nuclear chemistry. So atoms are unchangeable. That is the part that is false, because know about nuclear decay. And that nuclear decay is going to be really, really, really useful in making energy. And that's what we constantly, that's what we use it for in real life. And so that's what the rest of this, I'll just kind of talk to you a little bit about this one. The elements are going to spontaneously decay, and when they spontaneously decay, we capture that energy that they give off, which is very useful for turning turbines to make electrical energy. So everything, wind energy, water energy, nuclear energy, it's all about just spinning this little motor, and the motor makes electrons and pushes electrons through a wire. All electricity works the same exact way on the most basic level. So these things are called radioactive whenever they decay in this way. So radioactive decay is kind of the theme for today. So you got that first part. That should have been easy peasy. Okay, the rest of this stuff is just basically saying, why in the heck does this stuff decay? Well, it only decays because it's unstable. Okay, so radioactive isotopes are called radioisotopes. Write down these 2 pieces here, and that's it. Radioactive isotopes are just very unstable nuclei. So how are you going to get stable? You change. You change up the way you look. You change up the way your nucleus looks to become a more happier, more stable, lower energy isotope or atom. So, and fun fact, in the world, there's only, of all the atoms in the world, there's only 17% that are naturally stable. The other 83% are going to do this crazy radioactive decay stuff. So this is actually very regular, very common. And so when they decay, they kind of look like this. You can see the radioactive atom making energy, which we capture. We want this stuff because we need it for life and cell phones and stuff like that, and phones and the internet, right? And then the other particle gets shot off, and then we really don't care about that atom that shot off too much. But the reason that this is going to decay is because it's unstable. That's it. All right, I'm going on. All right, we already talked about this. So I'm not going to do this right here. And then we already talked about the high energy electron. Mass number doesn't change. We already saw that as well from our introduction from the table. So, yeah, we're good here. And then straight up energy, you probably remember it's the smallest wavelength, because like the radio waves are the really long waves, and then as you go all the way down over here, the little bitty waves are the gamma rays. Those are the smallest form of the electromagnetic spectrum. And they actually accompany all radioactive decay, but we don't write it every single time because it gets a little tedious to write down energy, energy, energy every time, when all of us know that nuclear decay is going to always emit energy, because that's one of the things of the perks of it, so we get to gather that energy up. So looking at gamma radiation again, the nucleus stays exactly the same. It's just this one's a little bit more stressed out and more energetic, so when it releases that energy, it's more stable form of the same exact nucleus. Thumbs up when you got this. Okay. I'm going to do half-life and fission and fusion. Fission and fusion, who's heard of those before? When do you guys learn this stuff? Is it 7th grade? 6th, 7th, okay, because your memories are a little bit more of that is closer than mine. Okay, so this one you don't need to write down. I have a highlight, but don't worry about it. I just want you to see that nuclear decay doesn't stop after that first little bounce chemical equation we made. It can keep going and going and going and going and going. So thorium emits an alpha particle and it makes radon. Yeah. And then it emits a beta particle and it makes actinium. And then it emits a beta particle and it makes thorium 90. That doesn't make sense, but yeah, maybe it is. Then it emits an alpha particle, then it emits an alpha particle, then it emits an alpha particle, and it goes on and on and on and on. It's a huge, long decay series. And it's going to keep doing that until it finally gets to a stable form, a stable isotope. So I like the picture form here better, because you can see, like, for example, uranium, which is used in chemical reactors, like Huntersville, that has a nuclear decay facility, not a nuclear chemistry facility, nuclear energy. So the uranium is going to continue down and form different forms of itself. And as it forms different forms of itself, it actually is going to be changing elements because it's changing the nucleus. It goes all the way down until it reaches a very stable form called lead-206. So it actually decays like 12 times to get to that point. So it doesn't have to only be one decay thing. It can be like 5 or 10, 12, 15. So that's called a decay series. Okay, transmutation, this word you should know. Transmutation. Trans means, well, yeah, what is trans, that prefix usually refer to? Change, to move, like transport means to cross, to travel. It's got a lot of different, that prefix means a lot of different things, but it means to go from something to something. That's generally what trans means. And that's exactly what's happening. We're going from uranium-213 to lead-206. So conversion of one type into another. To change form is kind of what this means, because change is the trans part, and mutation part is actually more along the change part, because that's like mutation of your genes and stuff like that. But essentially, transmutation means to change form, and we're specifying the nucleus is changing form in this case. So there are two ways. Yeah.
I was just wondering, the little chart on the last page,
Mm-hmm.
we have to know that before we attach?
No, that's just I wanted to kind of extend your knowledge a bit more on that. Okay, so the two ways that nuclei, or the nucleus of something, can change form are what we've been saying this whole time, nuclear decay, either by alpha, beta, or gamma. And that's kind of the trend we've seen so far today. Or, so this is the first way it can occur. The second way, this is a fun fact, but this is one, the first word I've underlined here, that's something you should know. It's called the particle accelerator. Think of, it's also termed the atom smasher. Shimmer. Shame. Atom smasher. Because that is exactly what's happening. They pretty much have a racetrack for atoms. It's in Switzerland. It's called CERN. I don't know what CERN stands for, but it's called CERN. And underground, they have I think it's 50 miles of racetrack. And what they do is they energize the atoms to a point, and they spin them around the racetrack that's underground for these atoms. And they're in these huge metal tunnels almost. And they pretty much energize them and spin them around, and they make them smack into each other. So they're smashing into each other. And when that happens, if they do it with just the right orientation and just the right amount of force, the two nuclei of atom 1 and atom 2, they fuse together. So do you think I'm talking about nuclear fusion or nuclear fission? Fusion, because they're smushing them together. When that happens, you get to make new elements. That's cool. And 2, you get to attain the energy from that. And that's essentially, that's really, really, really difficult to do. It's very unsuccessful because it's very hard to smush two nuclei together. You think you just go hey, do you guys mind combining? That'd be great. No, it does not happen very well. It does not happen very with high efficiency. So that's pretty cool because that's how we can make, we were talking about all the man-made elements that are underneath the transition metals in that one. Fleurium and LV, whatever that one is, Lucaburium, I forget what that one is. So that's how we make new elements. We just smush them together. It's not very easy. So you have to really bombard them to really overcome their natural repulsion for each other. So that's the second way to make a new, that's the second way to transmutate an atom. And so here's a picture of what it looks like a computer graphic image of it. So you have this one that's going this way, and another particle is coming this way, and they're supposed to meet in the middle. And when that happens, fireworks go because they're shooting off different particles, they're shooting off energy, or they just totally annihilate each other. It's like a big explosion. It's kind of fun. And that's the headquarters. That's just a picture. Okay, moving on. Fission and fusion. So the smasher, you just kind of heard is fusion. What we are talking about previously, alpha, beta, and gamma, that's fission. So I'm gonna let you write down all of these things, because this is one thing that we've not known about here. Scroll down a little bit, and then we'll talk about these. As you're writing, you're probably seeing they're in direct contrast with each other. They're exact opposites. start with fusion, since that's what we just talked about with the atom smasher. So that's pretty much what it sounds like. You put two nuclei that were smaller together, and you form larger things. So two small yields one larger one. That's essentially what's happening. But when that happens, they always release an immense amount of energy, okay? And that immense amount of energy is what we are seeking. And we humans, we're not that good yet. We cannot do a very good job. Like I said, the atom smasher is very inefficient. We are not very good at forcing two atoms together when they don't normally belong together. But once we get past that point of where we're deficient in our knowledge, we need to keep doing some trial and error, we need to keep experimenting, we will be like the sun. That is what the sun does every day for us to get the energy that we actually need, and the wavelengths that we need from the sun. So the sun does this by taking hydrogen atoms together, so hydrogen plus hydrogen to yield a helium. And when that happens, it creates the amount of energy that you see coming from the sun. That is crazy. But we want to be like the sun. We want to be able to get that energy. We're just not very efficient with that part of it yet. So fusion sounds like it is. Fuses. Two things come together. Fizz, think of fizz like bubbles coming out of a soda. They come apart from each other. That's the way I remember it. And that one also produces energy. And we can do that. We can totes do that. I mean, Homer Simpson can do it on The Simpsons. So we take one large atom, we break it into two smaller atoms, or three or four. I mean, it can fizz or diffuse into multiple pieces. But essentially, we take one large nuclide, which is what that is, nuclide, and we're going to make it into many pieces. And when that happens, also a large amount of energy is going to be released. We can actually capture that energy, and that's definitely what we use in nuclear power plants. So you need to know that. Fission is definitely what we use in nuclear power plants. Fusion is what the sun does. So know the examples that go along with them, okay? Thumbs up, ready to roll? Talk to me, people. You okay? Okay. All right, and here's just the same example. Fission, uranium-236 breaks into 4 pieces in this case. Fusion, 2 things come together to make a larger atom. It can then further decay, but we did succeed in making a larger atom. That's what that picture is showing. And then, there's just more pictures. Don't worry about that. And another picture. Okay, last topic, okay? Radioactive decay. So, I know, we've been talking about that this whole day, but the calculating aspect of it, the half-life of it. So this piece right here, you definitely need to know the definition of it now. I'll do this problem with you in one more. Okay, so after you see the definition, it's pretty clear on what this is, and this is, I think some of you have also heard of before, is half-life. The amount of time it takes, so half-life, the time, takes for half of a sample to disappear. And when I say disappear, we mean decay, we actually mean to change form, but a lot of times you've just said, okay, just ignore the fact that it was even there. So, for example, I can say the half-life of my pizza is 5 minutes. It takes me 5 minutes to eat half of pizza. So after 10 minutes, how much of my pizza is left? Huh? No, not. There's always something left on half-life. So if my pizza, there's my pizza, pepperoni and all, okay, it's 5 minutes for me to eat half of that. So after 5 minutes goes by, I have half of it left, right? Yeah. After another 5 minutes goes by, half of this is gone. Oops. So I have a quarter of it left, right? And after another 5 minutes goes by, half of that is gone. And after another 5 minutes goes by, half of that is gone. So you can see that the quantities get smaller and smaller and smaller, but In this case, I'm never going to finish all the pizza. It's going to get to a smallest crumb that I won't get. Okay? So that's exactly what happens with nuclear decay. Of the original sample we have, in this case, my example here, carbon-14. Of all the carbon-14 I have, after its half-life, which is very specific to whatever the heck we're talking about, carbon-14's half-life is 5,730 years. Okay? So the T1 half means time of half-life for half of it to disappear. It's going to take, if I have 100 grams of carbon-14, 100 grams, it's going to take 5,730 years for it to get down to half of that, which would be how many grams? If I said, and this is not an example, if I said I had carbon-14 and I had 100 grams of it, in 5,730 years, how much would I have left? 50. And another 5,700 and some years, I would have 25 grams, right? And another, how much would I have? 12.5 grams. And another half-life, how much would I have? 6.25 grams. And you can see it gets smaller and smaller and smaller. So if I said, all right, guys, I'm starting off with 100 grams of carbon 14, and you have to tell me how many half-lives have passed to get to only 6.25 grams left. How many half-lives have passed in this case? So 1, 2, 3, 4 half-lives passed for me to get to 6.25 grams for my original 100 grams. If I really wanted you to do some math, I would say how many years have passed for me to get to 6.25 grams. So what would you have to do? Yeah, 4 times 5,730 years, which is like, yeah, doesn't say like 2,300-ish years. Some change. You can keep going, but I'm gonna stop. Okay, so it's gonna take a long time. So I could ask you a question like this in many ways. So let me go with the example I have here because it's very mathematically minded. Okay, so carbon-14 emits beta radiation. Who cares? Decays with half-life of 730. So do an example with me. So just say carbon-14 T1 half is 5,730 years. Assume you start with a mass, so M, mass of 2.00 times 10 to the negative 12th grams. So I'm just kind of writing down my givens here. How long is 3 half-lives? Well, that's not really relevant to the mass part, but how long is 3 half-lives? What would I have to do? Right, so 3 times the half-life time, which was 5,730 years, which is 17... I have this for you. 17, actually for a 0, it was 23,000. 17,190 years. Okay? So after 3 half-lives, it takes that long to get to where the decay process is. Is it mine? No. Sorry. Yeah. Gotcha. Thanks. Bye. Okay, so that's how long 3 half-lives is. Now, how many grams of the original isotope, carbon-14, is left after these 3 half-lives? There's an equation that you want to write down for yourself, okay? It looks like this one, but I'm not going to use this equation because it's too complex, and that's something you'll learn in Algebra 2. I don't know if you've learned it yet. But it's the time, your mass final is equal to mass initial times 1/2, and then watch my exponent here. I have to be kind of funky with it. Let me see if I can move this up. To the power of time elapsed over half-life. I'm just going to put over T1 half, actually, because that's a little shorter. And I'll do this example. So this is the green part is a power, okay? It's an exponent. So mass final is what we're looking for after 3 half-lives have passed. Mass initial, we know, 1/2, that's just a constant, right? To this time difference here. So I'm going to write down all my knowledge, and we're going to calculate. So mass final is equal to mass initial, which was 2.00 times 10 to the negative 12 grams times 1/2 to the power of how much? 17,190 years is the years that were elapsed, the full time, divided by, I'm just going to try to put this in parentheses for you, divided by the half-life. Well, half-life is 5,730 years. So what's 17,190 divided by 5,030? 5,730. 3, right? Because we just did that. We just said 3 times 5,730 is equal to 17, blah, blah, blah. So can't I just raise this to the power of 3? It's the same thing as me doing that fraction. Yeah.
You just put the number of half-lives instead of
You can, if you know the full number, like for in this example, we know 3 half-lives have passed, so you can put that. But sometimes I'll say, in 100,000 years, how much is left? And if you don't know how many half-lives that is, you have to do the calculation. So I'm just giving you the tool to do it with, okay? So you can put 2 to the 17 blah, blah, blah over 5,000 blah, 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 or you can put 2 to the 3rd power, because that's how many half-lives have passed. Nathaniel, question?
Yeah, man.
Or to the 3rd. So when you do this to the negative 12 times 1/2 to the 3rd, you get 2.5. You get mass final to be 2.5 times 10 to the negative 13th grams.
Is the 2.0 times 10 to the negative 12, is that a required number that you have to put into this situation? Or is that
Yes, that is mass initial right here. Oops. Right here. That's what we were given in the problem. So that one, if that is given to you, you must utilize that. All right, so that equation seems not too hard, but is there an easier way to do this? Yes. And it just depends on if you can actually do it. So some people just forget how to do it. But this is the mathematical way to do it. There's also one where you can just divide by 2 3 times, because 3 half-lives have passed. So you can take 2.00 times 10 to the negative 12 grams. After 1 half-life passes, half of this disappears, right? So half of that disappears, so when you divide by 2, after the first half-life, you have remaining 1.00 times 10 to the negative 12 grams. All right, that's after only 1 half-life. Then half of that disappears, right? Okay, so after half of that disappears, we have 5.00 times 10 to the negative 13 grams left. So this was the first half-life remaining. This is the second half-life remaining. And then what do I got to do again?
Wouldn't that be point?
But I divided, it is 0.5 to the negative 12, but when I go from negative 12 to negative 13, I account for that. Because I moved the decimal back. Yeah? Good catch, though. Okay, so after the third half-life, we divide by 2 again, and there is remaining, guess what?
2.5.
Times 10 to the negative 13th, right? Grams. And that's exactly what we got when we did the harder math way, okay? If 15 half-lives pass, please do not divide by 2 15 times. It's going to take you forever. Plug it into that equation. Yes, ma'am.
Would it be okay if we were like 0.25 times 10 to the
Yeah, I'm fine with that. It's just not correct scientific notation, but I get your point. All right, so half-life, 2 different ways to do it. Divide by however number of half-lives pass, or plug into our lovely equation with the mass final, mass initial times 1/2 to the time elapsed over time of half-life. Okay, because sometimes the numbers are not going to come out crystal clear like 3. Okay, so let's try this one. Manganese 56 is the beta emitter. Nobody cares, but it's always going to be given to you. That part is not important. With a half-life, so T1/2 is 2.6 hours. What is the mass? So question, what is the mass final of manganese 56 in a 1? So we're given a mass, so we're assuming that's mass initial, right? We're assuming like the mass given to us is the first mass that we encounter. Mass initial of 1 milligram sample of the isotope at the end of, so time elapsed is 10.4 hours. So that's all of our given information. So let's see if we can do this little half thing. How many half-lives have passed?
5.
about or exactly? If it's not exactly, you can't do it. Okay, so 2.6 times plus 2.6 is 5.2. Okay, so 5.2 plus another 2.6. Okay, so I'm going to go with that too. So technically, yeah, 4, you got to make sure it's exactly, if you're going to do the whole divide by 2, divide by 2, divide by 2. So what I'm doing in my head, and you guys probably are too, 10.4 hours is the full time divided by the time of half-life, which is 2.6 hours. So that's 5.2 what we said, so this would be 4 times exactly. Did you just double check that for me? Okay, so 4 half-lives have passed. So we can go with our easy cheesy divide by 2 all the 4 times way, or we can plug into equation. So let's just divide by 2 4 times. So 1.0 milligrams divided by 2, that gives us, make that decimal a bit bigger, 0.5 milligrams. So that's after the first half-life. Then we divide that by 2 again, and we get 0.25 milligrams. That's after the second half-life. And then we divide that by 2, and we get 0.125 milligrams. That's after the third half-life. And then last one, we divide by 2 again, and we get 0.0625. No, 0.0625 milligrams. And that's after the fourth half-life, so we're stopping there. That's how much is left. So I find it sometimes easy. If you know a full set of half-lives passed, go with that. If you don't know the full half-lives passed, then go with your previous equation. All right, you guys are going to practice this some more in the lab, so you'll have a lot more mathematical practice. So have calculator out, have piece of paper out, and I'm going to tell you what you got to do with your activity. Oh, we have like 45 minutes left. This is nice. Okay. So the activity's fun. I'm going to skip the archaeologist part. It's the nuclear decay lab, okay? And it's called Skiddlium because I've made up this nice candy-related atom that's very radioactive. Now, you cannot eat the radioactive isotopes until they have decayed all the way. Okay? So after you decay them, they will be harmful to you if you eat Skiddlium stable isotopes. Okay? So the lab is really simple. You're going to see how many Skiddlium you have, and I'm going to have to combine two because I have a lot out there. 12 of you. So you're going to see how many Skiddlium you have. After one half-life, how much of this batch do you left? Half. And after that, half. So as they decay, you can totes eat them. But don't eat them until you know, because I know how many are in these boxes. Anyway, you're going to make a little chart, fill this out for yourself, and then there's a lot of questions. Get through as many questions as you can. There's a lot of practice on here. You can skip around so you can get to some, like, just word-based questions, and then there's some nuclear decay questions. There's some half-life questions. Skip around so you get a little practice on all of them, okay? So you guys can work in groups of 2. I think the number of groups of 2, and I'll bring you guys a second that is Skiddliums. You probably need a calculator. Yeah. Here's one group up here. Another group here. Another group back here. Another group right here. Another group here. Wait. Yeah. Yeah, groups of 2, I think that will work. If not, I'll go in groups of 3. Yeah, you guys can work in groups of 4. Groups of 2 work.
Keep on asking my parents for them to get their paper.
Nathaniel, you guys will keep your paper.
You. What's the sheet? Where's my note? Yes, I thought not.
All right, enjoy your time. I'm going to check your homework while you guys are labbing it up. No, yeah, I haven't checked it yet, so keep it all on your desk. Right there, yeah.
Oh, did you get his problem so far?
No, because I said I would look at it Monday, and then I didn't get a chance to because we were talking the whole time.
Okay.
So that's why I said to put it in your. You had, check. Yeah, this is pretty much everything I'm taking up. Whenever I say.
Can we write on this?
No, write on your own paper. That's why I said bring a piece of paper with you. Thank you. Thank you.
I don't know where I put my notes, I just had them. Oh, there they are.